tomorrow, I am out again. Tomorrow is part medical for me, part medical for my dog. We need to go get some surgery done on one of my pooches. So, hopefully he'll be fine. Should be all good. We're taking him to like a really good surgeon. So, tomorrow, those of you that look ahead in the homework things and start grabbing stuff, like Simon just noticed, he's like, wait a minute. In the rack there, where all like the future papers and stuff live, tomorrow's paper looks like it's 7 closure. Because it is. Because I don't trust our district, especially after yesterday, to have a sub in my room for me. Right? Luckily, Mrs. Gordon's awesome and she covered for me. And I heard you guys were great and you just did what you were supposed to do. Did anyone remember that activity, by the way? Had we done that or am I just crazy?
You had it, so some of my friends remembered it, but I think it was the thing you had is, if you have time, you can do this.
Okay. So, the closure has like 8 problems. You'll know how to do pretty much all of them, even though we haven't done the 7-3 section yet. So, again, I'm trying to help you out. Monday's homework was yellow. It gets turned in with yellow. If these are pink, here. And then we switch to blue. How many homeworks get turned in on the next homework collection? Only 2. So I'm trying to help you out, guys. I'm not trying to confuse you. We announced that back like last week.
But one of those
right? I know. It goes with the next set. Yeah, and like this for Friday is 7-3-1, but it goes in with the blue. Like 7-3-1 and the closure go together. Right? So whether or not you have a guest teacher here tomorrow, you're just gonna work. Like it'll just be work time. Just grab a closure, work on it. Don't do it like today at extensions or whatever, because then you won't have anything to do tomorrow, and that's silly. So, today's lesson, though, we get to talk all about proportional equations. Now, a lot of us may remember proportional expressions or proportions, like when we have a fraction equal to a fraction, or a ratio equal to a ratio. But proportional equations. As those of you working on homework right now, I can tell because the papers are colored. Please make the choice to put it away so I don't have to make that choice for you. Like, I'm talking to people that are like, I can see they're actively answering homework questions. Do you have an idea of what a proportional equation might be like, or what's like a situation that might spur a proportional equation? Time?
Equations that start out different but simplify to the same thing.
Okay. That value, like points from an equation that might, like when we reduce it, they actually equal each other. Yeah. Yeah. So like equivalent, like we talked about equivalent fractions, not yesterday but 2 days ago, right? So something that might like have equivalent fractions. Alex?
Would a proportional equation be if an equation didn't have if the equation only had a variable, then it starts at 0?
Only had a variable. What do you mean?
Like if the y-intercept point was 0 and it only went up.
So if I say we're gonna order pizza by the slice, just stick with me here. We're gonna have a food truck come, and I'm making this up, by the way. Don't anybody yell at me. We're gonna have a food truck come, and I'm gonna buy lunch for us. I'm gonna buy 3 slices of pizza for each of you, because it's like gourmet. Like you want to try, like the variety. They're not huge slices, but I'm good. So 3 for you, 3 for you, 3 for you, 3 for you. If none of us eat, how much pizza do we need? 0 slices, right? But if we want to talk about the pizza that we need, like if we say P is slices of pizza, thank you, smartboard. The pizza that we need would be 3 times the number of students, right? Or times the number of like people eating. That's what we're talking about with a situation that is a proportional equation. And what Alex was trying to get at is there's no plus something out here. There's no and some for the dog or some for like, there's no extra, it's just 3 per person. There's no other modifier. So, let's talk about some things that are oh so poignant this year, talking about leap years going with election years. Hey, it all ties together. You didn't realize I was asking that for a reason. So, Mr. Mears was running for mayor of Atlanta, and his campaign managers were eager to determine how many citizens of Atlanta would vote for him. So they decided to pay a respected impartial. What does impartial mean? Somebody raise a hand and help us out. What is impartial? Impartial, Charlie?
Impartial means to know there's no bias when picking.
Yeah, no bias. Statistical. What? Okay, so a statistical company. Who can tell me what a statistical company does?
Statistics.
Well, if you want to actually answer, raise your hand, Audrey.
They do statistics stuff, aka crunch numbers.
Ooh, crunch numbers. I will definitely take that. They essentially gather data, and by crunch numbers, we're not actually going to eat the data. We're going to put it together and be able to spit it out and essentially say, here's what we found out. Right? Here's what we found out. What? It's just bad jokes. I try to make bad jokes. So, these people calling to get that data are called pollsters. Okay? So because they are doing a poll, right? They're called a pollster. So not a pollstery, so a pollster. They call 100 people, and 68 indicate that they would vote for Mr. Mears.
Is that even legal?
Yeah, it's just a survey. I can call you and say, hey, what's your favorite pizza place?
And I can say rather not answer.
You can just hang up the phone. You wouldn't count in the 100. So this is they got responses from 100 people. That's actually a really good point to bring up. It's not just they just phone 100 times. This is got responses. And some people will say buzz off and like not answer your poll. You just move on to the next person. So
wasn't there like a really big goof with the calling people because they called them in the middle of the day and young people how old were they?
like old people that like weren't even going to go vote anyways or something. I think I know what you're talking about.
Because it was and so they thought the person was going to win the election, but in reality, the other person ended up winning the election.
By like a lot.
Yes.
Yeah. So you can look it up. If you search like pollsters get it wrong or something like that, you can probably find what Simon's talking about. So if instead they had called 50 people, then we could say, okay, well 68 out of the 100. But what would it be if it was out of 50? This isn't that hard.
34.
Not the same thing.
Almost the same thing. 24, 34. Give me my cube back.
I didn't do anything.
I wasn't even messing.
I don't care. Moving on, you guys have pretty much ruined it. Now the other teachers want to ban cubes. Please write this down in 2 minutes, and you don't have to write down like the whole sentence and everything. In 2 minutes, Stacy can write her name 17 times. How long would it take her to write her name 85 times? And this is where you're probably going to need a calculator. Use equivalent ratios to figure this out. Take like 2 minutes to try to figure this out.
You can only write 17 words in 2 minutes, though. 17 divided by 2.
Found it.
Guys, if you find calculators around the school, bring them home. I'm missing a bunch. Wherever you find appropriate. So really, just whatever you want. Was there actually a nice multiplication that we could do here? Yeah, 17 does actually work out nice sometimes. So it doesn't matter if we go 17 over 2 or 2 over 17. What matters is that our units agree. So if this is how many times she can write her name, then this is how many times she can write her name. So we put our 85 matching with the 17. We could actually build a ratio like this if we wanted to, and just put the 2 on top, and then we don't know down here. Same sort of thing. We can always cross multiply to solve, or if we're real good, how do we get from 17 to 85? Times, just shout it out. 5 actually works out here. So what's 2 times 5? 10. Now I don't know if this is still a thing, but last year when I taught this, Mrs. Goldring got all sentimental about when you had a crush on a boy, and who did she say it was? Terry.
Jim.
She said she would write her, not Jim, she would write her name over and over and over again in her notebook with like that person's last name. You know.
That's kind of obsessive.
You should do it 17
It's a
times.
thing people used to do. Nobody does this anymore.
No.
17 times.
No one's reading about marrying anybody anymore.
She do it 17 times to keep it back to the bear.
Ronald Fair. Ronald Fair was the sweetheart.
Fair.
So yeah, or my questionable decision. Are you gonna come over and talk about your love, or just talk over there? But that's not what matters, Mrs. Goldring.
Yeah, it's about the size of their heart.
It's not about
It's
love.
about the math. Oh yeah, I tried to do it when I
I used to write this.
So my questionable decision. Sit down. She'll inform us if we if there's something to be informed of. She'll inform us. My questionable ex-girlfriend Kristen would, and I'll save her last name, but she would write Mrs. Kristen Hudson. That's when I knew she was great. But no, when she, that's whoever was begging for crazy stories. I forget if it was anyone in this class. No, that's one that actually would have a crazy story to go with. But I was just talking with somebody about unit rate. What does unit rate mean, Logan?
It's basically, if it's like X to Y, then it's
Yeah, y when x is 1.
Whenever I'm faced with like one of these like proportional problems, I just find their unit rate first. It's like a great starting point.
Absolutely. So if we had 17 times that she could write her name in 2 minutes, Logan, if you said you already found it, what's our unit rate here?
1 to 8.5.
Yeah, 8.5 times that she can write her name.
And then you just gotta times that by 10.
You can't.
Terrible at multiply that.
So what does this actually mean, Xander?
You write your name.
You asked the question. Can you write half of your name? Yeah, you're in the middle of writing your name when the 60 seconds happens. You're halfway through. So you've written Zand, and you're halfway through the R, because that's the 5.5 letters, and then 5.5 letters. So,
Assuming that it takes the same time to write.
now, here's what I care about. And when Henry was bugging me about how big do we make our graph, I wouldn't really give him a good answer, and I'm sure he got frustrated at me for that. It doesn't matter how big we make our graph here. What we're trying to see is actually just one particular, well, kind of 3 things. Regardless of what we do with our graph, what is the independent variable here? Is it time, like time minutes, or times she's written her name? Josh? Is independent is the x-axis? This is like minutes, right? And then y.
We don't know if time's constant.
So guys, this is what we need to talk about. So those of you trying to make jokes or having side conversations, come back to me. Time moves on its own. Time does not wait for Stacy to write her name. Stacy writing her name depends on her having time, right? If she has no time, she can't write her name. So the time she writes her names, I'm going to put names instead of times because that's confusing. The time she writes her names depends on time. Right? Time is independent. Bear, sit in a desk. Come right up here between Bianca and Crystal. Can you guys move your thing so that Bear can sit in a desk because apparently gravity's too strong today? Thank you very much.
I didn't find a picture of him, but I found his address and everything. His
Oh.
wife's name is Paula.
Are you gonna go kill Paula?
What?
One time, like, I was staring, and I started asking, like, what, it's like I found out what Cooper first
Got his
got,
address
like,
and his
so I looked him up on the internet.
Call him.
I don't know why, but I remember that from last year. Like when I taught this, and you were like, "Oh, I remember writing your name over and over again." His first crush? My first girlfriend was Casey, but I don't think that really counts as crush. Simon? What? Oh, yes, it was times 5. Thank you. Hey, you should try to make your paper look like mine in the sense of this graph. Except I shouldn't draw that there. And we also found 1 8.5. We also found 1 and 8.5 there. And this is why I wouldn't really tell Henry how big I wanted you to make the graph or what we wanted to scale by. I don't care what's on those axes here, in this situation. What I care about is that you recognize 2 things that are happening here. 1, we've seen a lot, but it doesn't always have the other thing with it. Would these triangles all be the same?
Well, they're not.
Well, okay, but should they be?
Yeah.
Jerk. Fine. Fine. Fine, Liam.
That was
That was pretty impressive, actually.
No, now you're just trying to suck up. All right, Liam. Are these triangles all the same? Yes. So, the first thing you're looking for. Consistent slope, and you should write this down, which really we can see as straight line. You need to find straight line, and we've seen a bunch of straight lines already this chapter. We've been finding slope for a while. But what this has that a lot of those lines didn't have was the origin. The two things we will have when your graph is proportional is a straight line going through / coming from. Some people don't like it when you say going through, because this doesn't really go through, because it wouldn't. There's no negative time, right? So when I say go through the origin, what I really mean is it comes from the origin. 0, 0 is a point. 0, 0 is a point on our graph. 0 times 0 names. Henry?
Would a x equals 0 graph count as a proportional graph? Because it goes through the origin and it's a straight line.
No. Because the other, that's a really good question. The other thing that we have to have, truly, to be a proportional graph, and I appreciate that question. Well, we'd still have a y value there. What Henry's saying is like y equals 0 or x equals 0. Like, it'd just be always 0. You could just plug in whatever y, and if x is 0, doesn't matter what the y is. X is 0. There has to be consistent change that comes from a multiplying factor. So this, what's this multiplication? Times 2. So this has to be times 2. However, and this is where like x equals 0 wouldn't do this. What's this multiplication? Or crap. Go from the 100. It's easier. What's this multiplication? Yeah, 3.27. 3.27. So we do the same thing here. Your y must be please write this down, because this is what you need to recognize for the rest of forever. Yes. Your y, that's a k, but a lowercase k, because we don't often use capitals for equations and things like this. Hang on. Your y value must be some multiple of the x. So here in this table, if this is your y and this is your x, the independent variables, how many people we call, right? That's independent. I just pick up the phone and call. The dependent variables, how many people will actually vote for that dude? If I compare my y to my x, here, y is 0.68 x. Because it's 68% of the people we call, right? The people voting for Mr. Mears, people voting for him, is 68%, right, out of 100 of the people we call. So however many people we call, 68% of them, what we're saying is 68% should be voting for Mr. Mears. So if the amount of people we call is 327, we could just substitute 327. So we could do this multiplication, times 3.27. Or we could actually just find the equation that matches this situation, plug in our independent, Henry.
It's 222.
It's not 196.2, I guarantee, because 68% needs to be over half. Crap, no, that might be right. Did you do 0.68 times 327?
Yes, there was a decimal on the end, but since parts of voters can't go and vote, I decided not to include it.
You did 0.6? Are you sure you didn't type 0.86 or something?
Yes, 327 times.
No, not times. This is where we're getting goofed up. Let me just grab a calculator and double check. It's not times 3.27. It's 327. Yeah, it's 222. Okay, so whoever's getting 196 or whatever, it's 0.68. There are two different options here. You can't mix them. I can take 68 times 3.27. If I follow the red route, it's 222. Or I can come over here and go that's an eraser, not a pen. I can go to the 0.68. That's our multiplier. That's our constant of proportionality. And we're going to circle back to that word and plug in the x value, the amount of people we call. Now let's talk about the next vocab word we need to know. Constant of proportionality. Please write that down. I'm never going to ask you to write the whole thing down again. I will let you abbreviate it CP. But for now, you need to know what CP means, and it's not Cedar Point. Because when I see CP, my brain says Cedar Point. Seriously.
No, mine is combat powers.
I mean, if somebody says mana, I'm totally thinking Magic the Gathering, not like bread or anything else.
Wait, mana?
I'm thinking of Terraria.
I'm thinking of Magic the Gathering.
Why though?
I'm thinking of
All right, so the constant of proportionality is the thing, the number, the multiplier that relates x to y or y to x or however you want to say it is totally fine. So here, the amount of times, what's her name? Leslie, I don't know, whatever her name is. The amount of times Stacy can write her name, right? The number of names she can write down is 8.5 times the amount of minutes. Right? The amount of names is 8.5 times the amount of minutes. So wait. But we just called this the unit rate.
It is.
The unit rate is the constant of proportionality. They're the same thing.
Okay.
And why have two names?
Don't ask me. I didn't do it.
He's
You're right. So here's the thing, though. The constant of proportionality and the unit rate are only the same if it's a proportional relationship. You can have a unit rate and not be a proportional relationship. Because if I have to, give me your eyes, so I know you're actually listening. We go to, what's a good example? Where does it cost to get in? And then you can play games. Does it cost to get in?
Costco.
Chiller. Hey, we go to the chiller. Thank you. We go to the chiller. What's it cost to get into the chiller? $10. So what we're gonna pay to go to the chiller, our cost is $10 plus the arcade there, something to play.
Oh yeah, skates.
Okay. How much do skates cost?
Like $2.
$2. Well, okay. Let's imagine they have an arcade, and each game. I know this is falling apart because I'm making it up as we go. If we pay $2 per whatever, skates or game or what, like 2 is our unit rate. It is the cost per thing I do. Cost per skates or whatever it is the cost per. But because I have this 10, this is not a proportional relationship. This breaks it. This is still the unit rate. It's the cost per skate or whatever. But it's not proportional. This messes it. If Alina gets in for free and then only has to do, then it's proportional. Henry?
Never mind.
So pretend it's
Well, then there's a membership fee, and so then the problem is calculating. So, okay, I have a friend, Ryan. Ryan goes to Costco, and let's say he only goes once in the whole year. And he only goes to buy bags of popcorn. Chicago style, mixed cheddar and caramel corn, delicious. So, what Ryan paid for Costco
$60.
is his $60 membership fee, plus every bag of popcorn is $8. I mean, they're giant, right? They're big. So, is this proportional? No. Now, if they're trying to get your business, and the first year they're like, but wait, your first year is free. That's not really an X, I'm crossing this out. If you don't pay for the membership, and you just go pay for popcorn, is this proportional?
Yes.
Yes. And 8 would then be your constant of proportionality. And your unit rate, and your slope, and it's a bunch of things.
So I have 2 questions.
I have 2 answers.
Okay, we had to help that.
Just want to get to the railroad. I keep trying to go to the next slide, and you guys keep going back. But okay,
So, what is this is for 1 year, right?
Sure, yeah.
Okay, so that's my first question. And then, so constant of proportionality is only the unit rate if it's proportional.
Yep.
So,
If it's not, hold on, if it's not proportional, there is no constant of proportionality.
yeah, but is there still a unit rate?
Yeah, there's still a slope. So unit rate may not always apply in that situation, but we can always find the per one of something. It's like, let's say I'm talking miles per gallon.
Yeah.
They're like, in my car, how many miles can I drive compared to gallons of gas? That has a unit rate.
Yeah.
But I'd probably never just drive 1 gallon worth of gas. I probably drive less than that or more than that. Like, so it may not actually apply to that. Like,
Can you still call it a unit rate?
hmm? Well,
Take the car around the block to get
I mean, I can't really think of a
I mean,
lot
like,
of
you can call it a slope, which is easier.
We more normally call them slope. All right, we gotta move on
Why?
because future waits for no one.
No, that's I wasn't asking.
All right, this isn't gonna happen, but we're gonna try. So, Beth and her father have a large model road in their basement. Actually, if you guys ask me nicely and remind me, I may, try to find a video of a teacher that we all talk about a lot, Mr. Dove, who used to teach here. He was our social studies teacher. He has a model railroad. I forget what gauge, but it's pretty big, that runs through his yard. He has a whole path through it, and he's like, it's got like flowers and all kinds of stuff, and he put a GoPro on it and filmed like the whole route through the fence and like through these tunnels and stuff. So, if you remind me, I'll find that at some point and show it to you. But like, that's like discovery right there. Probably, but I'll find it. I'll show it to you guys at some point.
Are you on your New York route?
How long did it take this?
A while. He's been working on it for a long time. They also have like a smaller gauge model road in their basement, like that whole setup thing. It's just a hobby of his. So, Beth figured out that the equation y equals, hey, write this down, what I just highlighted, y equals 260 over 3 times x relates the length of an item on her model railroad to the length of the real thing, where x is the model size and y is the real thing, which makes sense because this is bigger than 1. This is going to make things bigger, right? That's a big number, 260 over 3. So that's how we get bigger. We could flip it over and come the other direction, right? But that's also, guys, to give it yet another name, it's our constant of proportionality, it's our unit rate, if we want to call it that, it's our slope, and it's also our scale factor. So if the model is 3 feet, how long would the real thing be? 260. This is comparing real to model. Logan? I mean, I'm going to call it lots of different things all the time to integrate like multiple vocabulary words. Alina?
So X is the size of the model, and then Y is
Yep.
the real.
Yep. Y is the real thing. So go ahead and make this table real quick. X, Y. Make an X, Y table. X.
Except
Why?
it doesn't make sense because Y should be the railroad or the model.
No, it shouldn't. It shouldn't.
Yeah, because X is the constant or the.
How big do we need it?
That's pretty sad.
We're saying the real thing depends on the size of the model. If I buy a bigger model, the real thing would be bigger. So get out of your head with thinking time moves on its own. The railroad can't change size on its own. We're relating the two things. If one thing changes, the other thing changes with it. So this is not like where we have time and something else. We have two
Good
heights.
afternoon. At the class change, could Ellie Keener please stop by the remote office? At the class change, Ellie Keener please stop by the remote office.
Right, that's okay. They might have made the model first. You don't know. I mean, a lot of things get modeled before they get made. You know what I mean? So the real thing, this is what what Bear's grappling with is good. He's saying, why is it this? Because the real thing depends on the model. That might be true. Right? You might have built the model first in designing this new thing, and then you scale it up and build the real thing, because you gotta think the real thing's more expensive. So, if we compare these things, like in our railroad set, right, you can't just have the trains, you gotta have some humans and some trees and some buildings.
Or you could just go to.
Wait, you can pay for humans?
You would buy. What? I'm confused what you're asking.
Wait, that's illegal.
Hold on. Crap. Beth's uncle's railroad is a different scale. We gotta figure out that scale. Now, finding that constant of proportionality is actually really easy. Just get your y and put it over your x. That's it. So if you want to write a reminder for yourself, this will make a lot of sense to some of you and take a minute to click for other ones. And it's just how your brain works. Y equals y divided by x times x.
So Y equals Y.
Y equals y.
Water is wet.
Because if x is over 1, an x on bottom and an x on top cancel each other out.
So Y over 1
So our equation of y equals mx, that m, really we normally talk about delta y and delta x, but when you're just given a y and a x and x, we just use those. And we assume if the model height is 0, what's the real height? 0. So actually, technically, guys, if we put a 0 up here and a 0 up here, this is delta y, and this is delta x, the change. Because if we go from 0, 0, my change in y is 60. My change in x is 0.94. People over here do 60 divided by 0.94. People in the middle do 300 divided by 4.7. And people over here do 480 divided by 7.52. Let's see if we all match. People over here do the top. People in the middle do the middle. People over here do the bottom. I hear a 63.83.
That's rounding edge time.
Yeah.
829787.
That's what we got. We got the exact same thing. It's probably repeated.
Who knows? Honestly.
It's gross.
Because this only goes so far.
So, notice, this is in decimal notation. It's gross. If you hit, anyone still have this on their calculator? There's a fraction decimal conversion button that lives second table. Hit enter, see if it works. Second table.
Yes, it does.
This F to D, what is that fraction?
3,000 divided by 40. Oh my
simplest.
No, stop simple.
Yeah. That's as reduced as we can get it. That's as reduced as we. But I don't put decimals in fractions because that's gross. So this, in my book, is better. But either of these are the same. That's all the time we got. Get out of here, guys. Have a great day.
Yeah. Wow. Great. Great.